Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be right away starting our discussion on the acceleration formula. So acceleration transformation formula. Okay, so what we have is dv dt at f is dv dt at f. So this is our velocity. So this is the velocity in the fixed frame. So velocity in fixed frame, and this is the velocity of the frame. And then the next is dv prime dt. So the third one is the velocity in the velocity in the moving. In the fixed frame, the velocity of the moving object in the fixed frame, right? So this is the net velocity. So this is straight again our relation number 1. So now this is so this is the translational velocity. So this is we are starting our discussion from relation number 2, that is the velocity transformation formula, that is this quantity here, right? So so coming back, we see that this is dv d prime dv dt prime plus the second quantity is coming from the rotational part. So d omega dt at f cross r prime plus omega cross dr prime dt at f. Okay, so omega cross dr prime dt at f. Okay, so then what we have is, let us now simplify this whole discussion. So from our relation 1, the velocity transformation formula 1, so from relation 1, hold on, so that comes later here. So now, so what are these different quantities? These different quantities are acceleration. So let us denote it by small a. So the acceleration of the object in the inertial frame is the acceleration of the frame. So this is capital A, is the acceleration of the frame, plus dv prime dt at f plus omega dot cross r prime plus omega cross dr prime dt, right, at f. So this is omega dot and this, fine. So these are the various quantities. Okay, so now, so from our relation 1, the velocity transformation formula 1, we can now substitute this quantity. So we see that we have that dv prime dt at f is dv prime dt at f prime. So we are substituting this quantity. Again, we are recapping our formula 1. So plus omega cross with v prime, or this is also equal to acceleration in the frame f prime plus omega cross v prime, right? So now we plug everything in this relation back, and we see that our net acceleration of the object in the inertial frame, that the fixed frame, is equal to the acceleration of the frame, and then plus this quantity here, this is omega dot cross r prime, and then plus we are now going to club some terms. Here we have omega cross v. So omega cross v plus omega cross omega cross v is what have we got? Omega cross v prime is this quantity, and then omega cross r prime, right? So where is this quantity coming from? We have this is this is coming from formula number 2. So this is from formula number 2 we are getting. So this is with respect to this formula here. The formula 2 here is this quantity here, right? Okay. So then what we have is plus a prime is here, and then plus omega cross v prime, right? Omega cross v prime. Okay. So we have clubbed all the terms together after using formula 1, the velocity transformation formula 1, the velocity transformation formula 2, and we see that there are these various terms. The first term, this quantity. So I'm going to again rewrite this. So this is a plus omega dot cross r prime. So this is the acceleration in the of the object in the fixed frame. And then there are these new quantities omega cross v prime, and then if we distribute this cross of omega, plus omega cross r, right? So this is omega cross r prime, right? Plus a prime plus omega cross v prime, right? So we see that this quantity in the literature of physics, in the literature of apparent body dynamics, is denoted by the so-called Coriolis term. So the Coriolis term. Now, typically these Coriolis terms are these are not new force terms. These arises because we are looking at the object under consideration in a frame of reference which is fixed. Now, if we look at the same motion of the object in the moving frame, all these Coriolis terms and the second term, or the so-called centrifugal terms, they vanish. So this term is the centrifugal term, right? So they all vanish, right? So now let us recap. So we have come to an interesting stage here. So we are now looking at the particle dynamics in non-inertial frames. Particle dynamics in non-inertial frame, and we see that the second law in the non-inertial frame is m of a plus omega dot cross r prime plus 2 omega cross v plus omega cross r prime. Okay, so plus a prime, and these are the different terms we have written from the previous statement, and this is equal to the net force experienced by the object in the fixed frame of reference. So we are again denoting our r prime, v prime and a prime as our apparent position, and our v prime as our apparent velocity, and our a prime as our apparent acceleration, right, of the particle p in the frame f prime. And our quantities capital A and capital omega and capital omega dot are the translational acceleration of the frame. So this is the translational acceleration of the frame. This is the angular velocity, and this is the angular acceleration of the frame, right? So of the frame f prime with respect to f. So then this is all what we have. So let us now understand this entire setup with an example. So the example that we have is that we have a roundabout and we have an object which is moving in the roundabout, and we want to find the net motion of that object in some fixed frame. So the problem says a roundabout is made to rotate with constant angular speed. Omega about its fixed axis of symmetry, fixed in vertical position. With anti-clockwise rotation. A man is on the roundabout. And is walking towards the center O prime, and moving along. I have to write this and then I can draw all these figures, and moving along radius A prime O prime with constant speed v. So this question says, what is the force the roundabout exerts on the man, Okay, so the diagram is fairly simple. So we have a circular disc or a roundabout which is rotating. So let us say the rotational axis is this vertical axis and the rotational angular velocity is omega. It is given here. And then let us denote this vertical axis as our E3 axis. And now we can fix some fixed axis, let's say E1 and E2. And we see that E1 and E2 now, this is a fixed axis, some fixed frame. And now we can have another frame of reference. Let us say the body fitted frame, which is E1 prime, E2 prime, E3. So the frame E1 prime, E2 prime, E3, I remove this prime here. So our frame E1 prime, E2 prime, E3. See, E3 is always fixed, whether you look at fixed frame or body fitted frame. So in the body fitted frame, we have this quantity which is this is what we have the frame. Okay, so then the frame is attached to the roundabout. This is attached to the roundabout. So this is our moving frame. Now in the moving frame, that there is a motion of the man which is towards the center. So let us say this, we denote this as O, and let us say we have the man which is positioned at A prime. So our O and O prime, they coincide. So the man is moving towards the center O prime, or which is also O. Now, so in in F prime we have zero translational velocity, and constant angular velocity. So omega is omega of E3, and what we have is the frame F is given by the frame is such that it is just rotating with a constant angular velocity. The frame F prime is rotating. So with respect to F, we have the frame's acceleration and capital A and capital omega dot, they are all 0. So in this fixed frame, the acceleration of the rotating frame is all 0. So then so what are the different forces which are acting on the man? So one is of course the weight of the man. So weight, let us say mg E3 with a minus sign. So mg E3 with a minus sign, and then let us say this object, it exerts the roundabout due to Newton's third law. Because of the weight of the man, it is going to exert some force. We don't know what is the direction of the force, so let us call this force as our x force or x, right? We don't know the direction, it's just a vector. So now let us write down the force balance. So what we have is the following. So in my moving frame, what we see is my position vector of the person is changing, let's say x1 E1. So the person is moving towards the center. So we can denote our E1 direction as E1 prime direction as our radial direction, or pointing towards the center or moving out of the center, radial direction, right? And then our velocity v prime is minus v E1 prime, and a is 0. A1 prime is 0. Okay. So a prime is 0. So there is no acceleration in the moving frame. So then in the second law, we can write down the force balance in the moving frame. So we see that the net forces are the velocity of the man. So we have 2 omega E3. So we are writing the force balance with respect to the fixed frame F. So 2 omega E3 cross with minus v times E1 prime, and then plus omega E3 cross with omega E3. So these are the various components of, so this is the centrifugal term which I am writing, and this first term is the Coriolis term, and cross with x1 prime E1 prime, right? So this is also equal to minus mg E3 plus x, right? So mg E3 plus x. So now x is mg E3. We see that x is our unknown force. So now we can regroup all the terms on the left hand side to find out this unknown force x. So x is the quantity which is coming from the weight of the man, minus this particular quantity, we have to put an m, the weight as the mass as well. So this is minus 2m omega v E2 prime minus m omega square x1 E1 prime. right? So minus m omega square x1 E1 prime. And so this is what we wanted to find, the force exerted by the surface on the man. We see that this quantity is our so-called Coriolis effect. Our Coriolis effect, and this quantity is our centrifugal effect, right? So these are the various terms. So now, I just want to again highlight that these are not new terms so far. We have only looked at the Newtonian mechanics in inertial frame. Due to this moving frame, these are the new terms which are arising, but they are fake terms. These are the so-called fictitious terms because of the moving reference frame that we had incorporated. So fictitious forces in moving frame, right? So if we take the moving frame itself as our frame of reference, then these terms will vanish, right? So that is what we have. So an example which is seen in our everyday life, let's say the example of a projectile motion, the motion of a ball which is thrown from the surface of the earth, right? We know that earth is also moving with time, right? So we have that motion of earth, motion of let's say projectile with respect to earth, right? So what we have is, we have the earth, and we know that the earth is also rotating. So let us say the rotational axis of the earth is so this is the north pole of the earth, and let us say the south pole of the earth is S. So the rotational axis of the earth is omega, is given by omega times the Sn axis, the south north pole axis, right? Now then what we have is, let us say the projectile motion is on the surface of the earth. Now since earth is not flat, we expect that let us now put a frame of reference on the projectile motion itself, or the body whose dynamics we want to see. So now this frame in which we are looking at the body's motion is our moving frame. And let us now denote this frame with frame E1, E2, E3, right? We see that this frame E1, E2, E3, they are the moving frame. And now since this is not on a flat surface, this frame is going to subtend an angle with respect to the diameter of the earth. Let us say this angle is beta, right? Typically beta is 90 degrees minus theta, where theta is the latitude angle, right? And then what we have is the following, that so beta is, here is also again beta, and now we want to look at the motion of some particle P which is experiencing some velocity v, right? So that is the setup. So we want to see, the idea is we want to see the effect of the orbital motion, right? So then see, this is the eventual goal. We want to see the orbital the orbital rotation, right? The effect of, the earth's rotation. We want to look at the impact of the earth's rotation on the projectile motion, right? We also know that earth has two sets of motion. One is of course the rotation about its north-south axis, and also it is revolving around the sun, around the soul in the solar system. So that is the orbital motion, and that is its angular frequency or angular velocity is very small compared to its rotational angular frequency, right? So we can neglect, so we are going to neglect the orbital motion around the sun. Neglect orbital motion around sun because this is negligibly small compared with the orbital rotation of the earth. So then, so what we have? So we assume the earth is axially symmetric rigid body. So we assume that earth is a perfect sphere, right? So then we are assuming axially symmetric rigid body. Now, what do we mean by axially symmetric rigid body? We are going to look at this concept in 1 or 2 modules later, right? And then let us now denote our frame f prime. This is our frame f prime. F prime as our frame O comma E1 comma E2 comma E3, which is rotating, which is spinning with the earth itself, right? So this is the non-inertial frame, which is the non-inertial frame. We need to be very careful with the choice of words here. Well, why we call this as a non-inertial frame? Because for the projectile motion, this seems fixed. But with respect to Earth's rotation, this is moving, right? So still we denote it as a non-inertial frame to begin with. So non-inertial frame attached to the surface of the Earth. Frame attached to the Earth's surface. Attached to the Earth's surface. Okay, so then what we have is the acceleration A. So what do we get? So now if we were to find the rotational speed of the Earth, the rotational angular velocity, we can do that. So the angular velocity of f prime. F prime is identical to that of the rotational angular velocity of Earth. The rotational angular velocity of Earth, omega n, right? So where n is Sn by norm of Sn, right? So this is our n. So this is our n axis. This is the case, right? So n and omega is 2 pi radians per day. So we expect the Earth is revolving. It is going to spin. When we go from day to night, it is going to spin 360 degrees, 2 pi radians in one day. And that translates to, when we translate day into seconds, that translates to 7.3 into 10 to the power minus 5 radians per second. Right? Radians per second. Okay. So then this is what we have. So now we want to look at the motion of this object P in this moving frame that I have drawn. So I call this moving frame F prime here, this frame. So let us see that. So according to the second law for P, this is in the moving frame. In the moving frame, F, or the particle of mass m, is going to, so the mass of the particle is m. So m is A plus 2 omega cross V plus omega cross R plus A. This is F external. This is the external force being acting on the object. Typically, it is going to be the weight of the object. So again, our these quantities R, A, and V. These are now I have dropped the primes, but these are apparent quantities in the projectile frame. Apparent quantities in the projectile frame, right? And this is typically the gravitational force exerted on the earth itself. And now we see that A naught is M inverse F external, M inverse F external minus A minus omega cross R. So I'm just transferring all these terms on the other side, minus A cross omega cross R, and this is also equal to this minus A minus this quantity minus, so I have transferred all these terms, the Coriolis terms, this centrifugal terms on the right hand side, and we are left with, let us say we are trying to find what is at the condition at t equal to 0. So this is at t equal to 0. So we expect that the particle is at rest, and let's say the r is the position vector. The r is the position vector, right? So so A naught is going to be minus. So this is the net weight of these are the net forces acting on the particle, and this is at t equal to 0. Our moving frame A is A naught. Acceleration of the moving frame will be A naught at t equal to 0, and typically these are all clubbed into so this is divided by m throughout. So this is g times, so this is the acceleration due to gravity times k of r. So what I am trying to say is, if we neglect the Coriolis effect, right? So what have we got here? So we are looking at so at t equal to 0, the particle is at rest. So this means V is 0. So this term is 0 here, and we only get this term here, and minus A is here, and so we are finding the initial acceleration. Right? And now what we are saying is that, look, if we did not consider the Earth's rotation or the acceleration of the moving frame itself, which is connected with the Earth's rotation, then the net force experienced by the particle is m times g, right? Weight. But now the acceleration due to gravity is slightly modified because of this rotational forces, the spin of the Earth, and so this is our new approximate acceleration due to gravity. So we will keep this formula as it is. So this is our new weight of the object, taking into account the acceleration effects. So now what we have is, so looking back, let us call this relation as star. So from star, what we have is that m times dv dt, this quantity that is the acceleration of the frame, plus 2 times omega cross v, which is this quantity, and the rest is all absorbed in g times k. So this is equal to minus m g of r k of r. So everything, this quantity is all absorbed in the weight, in the acceleration due to gravity. We multiply by m, so we have the effective weight of the particle. So this is our equation of projectile motion equation, right? And we call this, we are going to keep this equation as our equation number A, and whenever we want to study the object, the motion of an object, taking into account the Earth's rotation, we are going to use this equation of motion A. So this is our new Newton's second law, taking into account the effect of the Earth's rotation, right? All the other effects like Coriolis effect, the centrifugal effect of the Earth is all absorbed in this approximate G relation, right? So that is the end of the discussion here, and we are going to see what happens in the next. We will start with some examples. So thank you so far for listening.